Greetings, fellow explorers of the digital frontier. Ernis here, ready to embark on another mind-expanding journey through the latest in AI research. Today, we're diving into a fascinating paper that tackles a critical challenge for vision language models, or VL as they're known. These models are like the Swiss Army knives of AI. Trained on massive datasets of images and text, they can perform zero-shot generalization, meaning they can recognize objects and concepts they've never explicitly been taught. But, as with any tool, their performance can falter when faced with unfamiliar situations. Imagine you've trained a VLM to identify different species of fish. It works flawlessly on the pristine, curated images it was trained on. But what happens when you throw it into the murky depths of real-world data? Suddenly, our model might struggle with oddly lit photos or images where the fish are partially obscured by seaweed. This distribution shift, where the data the model encounters in deployment differs significantly from its training data, is a major headache. It's like teaching someone to drive in a perfectly simulated environment and then expecting them to navigate the chaotic streets of Mumbai without a scratch. Now, the paper we're dissecting today introduces a clever solution to this problem, a framework called Class-Aware Prototype Learning with Negative Contrast, or CP for short. It is a mouthful. But trust me, the ideas are pure gold. This framework is designed to adapt VLM to these distribution shifts during test time, meaning it adjusts the model on the fly using in-labeled target data. No extra training data required. Think of CPL as a skilled adaptive artist. It's like that artist is constantly refining their portrait as the light changes and new details emerge. The secret lies in two key modules: the class-aware prototype cache and the negative contrastive learning mechanism. Ready to explore each of them? First stop, let's step inside the class-aware prototype cache. Imagine this cache as a cosmic filing cabinet, where each drawer represents a different class of objects. Dogs, cats, cars, you name it. Now, here's the twist: the size of each drawer isn't fixed. Instead, it dynamically adjusts based on how frequently that class appears in the test data and how recently it was seen. It's like a bouncer at a cosmic nightclub, controlling how many representatives of each class get to hang out inside. Why is this important? Well, in real-world scenarios, some classes are rare. Imagine trying to identify different species of mushrooms in a forest where only a few rare species pop up sporadically. A standard cache might quickly forget these rare species as it gets filled with more common fungi. But the class-aware prototype cache has a clever trick up its sleeve, a rejuvenation mechanism for inactive classes. It's like giving a shot of espresso to those forgotten prototypes, injecting them with synthetic features borrowed from visually or semantically similar categories. It's basically saying, hey, you might be rare, but we still remember you. Now, let's move into the next room of our memory palace, where we find the negative contrastive learning mechanism. This module tackles another critical challenge: distinguishing between semantically similar classes. Think of it as a cosmic referee, ensuring that our VLM doesn't confuse a starfish with a goldfish. After all, they both live in the ocean, but they're quite different creatures. The negative contrastive learning mechanism works by identifying the most similar but incorrect visual-textual prototype pairs and then applying an INFO loss to explicitly separate these confusing classes in the embedding space. What that means is that it takes the prototypes for goldfish and starfish and actively pushes them apart, making it easier for the model to distinguish between them. It's like teaching a child the difference between a square and a rectangle by showing them examples of both and highlighting their key differences. You might be wondering, why not update both the visual and textual prototypes? Well, the authors found that refining only the textual prototypes while anchoring on stable visual features leads to better performance and stability. It's like fine-tuning a musical instrument by adjusting the strings while keeping the body of the instrument fixed. Now, the authors put CP through its paces on a battery of 15 image recognition benchmarks, and the results were impressive. CPLNC consistently outperformed existing test-time adaptation methods across both ResNet 50 and VISLASH16 backbones. That's like saying it won the gold medal in both the decathlon and the heptathlon of AI. So, what's the big takeaway here? CP offers a robust and efficient solution to the problem of distribution shift in vision language models. By dynamically adjusting cache capacity and explicitly separating confusing classes, it enables VL to generalize more effectively to unseen data. And that, my friends, is a giant leap for AI kind. This paper is not just a theoretical exercise. It has real-world implications for a wide range of applications, from image search and object recognition to robotics and autonomous driving. Imagine a future where our AI systems can seamlessly adapt to any environment, any situation, without the need for constant retraining. That's the promise of CP. So, go forth, explore, and keep pushing the boundaries of what's possible. Until next time, this is Ernis, signing off from Paperledge, your guide to the cutting edge of academic research.